Without further ado, I'd like to introduce Dr. Francisco Diego from University College London, Celestial Shadows, Terror, Myth, Science, and Beauty. Please join me in welcoming him.
Beautiful is your rising in the horizon of heaven, you living God. You who were first at the beginning of things. Your rays reach the lands to the very limits of all what you have created. You are beautiful and great and shining. We used to welcome the sun every morning for thousands and thousands of years, realizing how important it is. We build monuments. We build poems, we write poems, beautiful poems, beautiful philosophy. We know that without the sun, there wouldn't be life. That amazing thing that is in the sky for us, all the time, without which we wouldn't have food, without which we wouldn't have light and heat. All life depends on the sun. If we go back in history, we find every single culture representing the sun in different ways. This is one of my favorite ones. It shows a shower of flowers coming from the sun to humankind. And I don't know if the Egyptians knew about quantum physics, but what you see here is photons coming from the sun to humankind. And each photon has different frequency, different energy according to the color. So isn't that amazing? You may claim alien intervention here. It is amazing what they did. The sun appears wherever there is a deity. Akhenaton got rid of the gods and then just to worship the sun itself, and first attempt of monotheistic religion. And we find the disk of the sun on top of the heads of all these gods and goddesses, even animals. The tombs are decorated with the sun, a symbol of kind of eternity. And we have sort of borrowed, to put it in a kind of sweet way, to borrow the sun from the Egyptians to our sacred figures as well. We see the sun around the heads of the virgins and the Jesus Christ and all this. You have always this thing in the head. Amazing inheritance that we have culturally from our past. Now what happens? The sun, I said, is always there in the sky for us. Is it? Occasionally, it's not. It comes to the point that the sun disappears in the middle of the day, terrifying everybody witnessing that horrible thing. You know when the sun disappears. You don't know if the sun is going to disappear for a few seconds, for a few minutes, for an hour, for a week, or forever. And you feel that. It gets dark. It gets cold. This is a very famous representation of a battle in the Middle East that was taking place at the moment of the disappearance of the sun. According to this historical record, the battling parties signed an armistice because of this. You may say, well, that's it. All we need is solar eclipses, and then the world will be much more peaceful. So, and then we come with our myths. This terror that we have invites myths. Every time we are terrorized by volcanic eruptions, by something which is threatening our safety, our security on this place, we invoke myths, we invoke gods, we invoke an explanation of what's happening. For the Chinese, it's a dragon that is going to come and eat the sun away, and that dragon is converted into a kind of jaguar for the Maya, because that's the kind of animals they had there. And this comes from India. You will find this statue in the British Museum. It is the god Ragu. The god Ragu, well, he was a very nasty character according to this mythology. He wanted to get eternal life. And when you want to get eternal life, you have to drink the magic potion. And where you find the magic potion? Well, you have to go to the dinner of the gods. So they're having dinner, they're having drinks, etc. And he comes disguised as a woman, I understand. You may correct me, you may know the story. And he steals the potion from the table and starts drinking it. At that point, Vishnu, the father of the gods, just discovers him and chops his head off instantly. That's what happens if you do that. And throws the head into the sky. Since then, in revenge, the head of Ragu is going to go over the sky and eat the sun and the moon. But not for very long, because he hasn't got body, swallows it, and then comes back again. Well, let's now move from the myth and terror to the science. We are going to go like the adventurous traveler here and understand how the things work, really, because that's the power that we have today. That beautiful thing that we have in the sky is very mysterious. We look at it with our special filters, and we find amazing things. The first one is that we know that the sun is very big. It's 100 times bigger than the Earth. We know that the moon is very small. It's four times smaller than the Earth. Therefore, the moon and the sun are 400 times different in size. But by chance, it happens to be that the sun and the moon are at a distance, a relative distance of 400 as well. So the distance and the sizes compensate in such a way that we see the sun and the moon the same size in the sky. And because of the formation of the solar system in a single plane, they more or less come in the same plane, and we have the chance to see them with the moon in front of the sun, much closer. And this is what happened. So it's not a dragon, it's not a Ragu or a cosmic jaguar, it is the moon. And the moon comes and blocks the sun in particular places. The alignment is very precise. It's a matter of a few kilometers that you have to be there when the alignment is perfect. And you know, I have been in this place many times. And every single time, when it comes to that point, you kind of feel that fear. You see? It's still there in us. You see, this was in China. You see that shadow that comes from the left here at twice the speed of sound, more than 2,000 kilometers per hour. And it's going to sweep your landscape in a matter of seconds. And the temperature drops. And here we are with our telescopes and stuff, and we are just like this. Forget about all what you need to do in that short period of time. So we remember that some way, somehow. I play you this video. This is in real time. You see the movements of the clouds. The clouds are going to the right. The shadow of the moon is coming from the left. You will see the darkening, and now at that speed, the landscape goes down, and you are surrounded by twilight, 360 degrees around you. And that's the fear, and that's the enormous, it's a sense of being possessed by a force that we cannot control. That is the explanation for all this terror and all these myths that we have. Eventually, yes, the shadow moves away. You can see the bright part of the sky now as the shadow leaves, and then our landscape becomes illuminated again. Isn't that amazing? From space, you can see the shadow of the moon projected from the Mir space station, I think it was at that time. And that's how big it is. It's about 200 kilometers on average in diameter. All that is happening in our landscape, and at the same time, simultaneously this is happening in the sky. What you see here is a video that shows the last bit of the sun, which is being filmed with a filter. And at this point, what I do is remove the filter and let the light, unfiltered light from the sun, risking burning the camera because it was a bit early. But then you will see in real time what happens. This is real time. I will keep quiet so you can appreciate what's happening. Isn't that amazing? What you see here is the inner part of the solar corona. You see the pink color of the chromosphere that we're going to see later on. But this is happening exactly at that time, at that pace, simultaneously with the whole thing in the landscape around you. So you are looking at the two things at the same time and trying to control the camera, so you see a bit of shaking there as well. This is another landscape that we filmed in Easter Island. There. This is a faster motion. Right, complete. Look at the landscape, at the crater here at the bottom. And then coming back. So it speed up about 20 times, I think, from what it was. In the sky, what happens simultaneously is the emergence and the words of people that have been moved by this amazing experience, the appearance in the sky of a cosmic flower, the solar corona. The solar corona is very faint. We don't see it in normal conditions. We need very special techniques to see it, but not in this way. We really need to block the sun from outside of the atmosphere, only in a solar eclipse, to see that cosmic flower. That, in the eyes of in our ancestors, it was terrifying to see like a threatening eye looking at you, because obviously you have done something wrong, because we always do, and then you feel threatened by the eye. And this is the terror there, the solar corona. So that landscape that we have there when the shadow of the moon is coming, now it comes, and with the corona there, a bit of clouds and this twilight, and we see Mercury and Venus here probably, and we see bright planets and stars during that darkness that comes so suddenly. This is a computer simulation of a total solar eclipse when we see a few bright stars. We never see the sky that dark, but this is just to give us a guide of what to look for in the sky during the totality of the eclipse. In this picture, we have the last bit of the photosphere of the sun, which is the bright part of the sun. We see the chromosphere here in this beautiful pink color. I'm going to explain why this color is pink. This is called the diamond ring for obvious reasons. Appears before and after the totality. This is another view of the diamond ring with the inner part of the corona, very short exposure, and some bits of the chromosphere here. What I show you now is the diamond ring in a movie made through a diffraction grating. So what you see here is still with a filter, is the spectrum of the sun, which is the rainbow essentially, through the diffraction grating, still with a filter because this was very bright before the I remove the filter, and now is the light of the remaining part of the sun, which is being filtering behind the moon, and now the moon is going to cover that little bit of the photosphere and see what happens. All this is filled by light, it's all saturated, but the light is decreasing all the time, and you see here what is the spectrum of the sun, which is spread out into colors by the diffraction grating, and as the photosphere disappears, we see the rainbow here that is going to be changed. We start looking at bright things here. There is a bright thing here, another one here, another one here. You see these bright lines there. That's the spectrum of the chromosphere, which has hydrogen, which is this one. It has helium, which is this one, more hydrogen. So the combination of these three lines, which is blue, red, and yellow, give you the beautiful pink color. You see? Red and blue. Purple, and the yellow in the middle. The yellow line that we saw here was helium, and the first time it was observed was in the late 1800s, and that's how helium was discovered. This is why helium is called helium, because Helios, the god, the sun god. We still have a couple of prominences here, deep into the eclipse, is still showing the hydrogen alpha radiation there. Let me just move forward. Okay, so we have the chromosphere here and some prominences. The chromosphere is not homogeneous. It is modulated by magnetic fields, and sometimes the material bunches around the magnetic fields and produces the prominences here, which is exactly the same thing, the same color, and we see the prominences there. Now, if we explore the solar corona, there are so many pictures now taken with modern technology, modern image processing to compensate the variation of the luminosity of the corona, and we see amazing structures there. And this exposure is so deep. I mean, there are probably 100 different types of exposures here. The longer exposure allows us to see details on the surface of the moon because we see the earth shine. We see the earth shine coming from the earth, which seen from the moon, the earth is full, and the earth is very bright, so it sends a lot of light back to the moon, and we can see that during the total solar eclipse. So, in a way, this is the dark side of the moon. Okay?
That's seriously cool,
Huh?
That's seriously cool.
It is, absolutely, yeah. But you see what's happening in the poor solar corona, and remember, the scale of the sun, if the Earth was this distance, the Earth will be the size of my laser pointer there. That's the size of the Earth. So these are huge, huge structures. You see evidence of magnetic fields all over the place. Some material has been detached here and is flying away. All this material flies away at hundreds and hundreds of kilometers per second. And you see a lot of waves here implying enormous dynamic structure there. The solar corona is 2 million degrees. And still, there is no proper explanation of that. The solar surface is only 5,000 degrees or 6,000 degrees. The solar corona is 2 million degrees. And the way the temperature goes up is still to be explored, but certainly magnetic fields have a lot to do with that. And this is one of the reasons we observe solar eclipses all the time. This is another amazing picture with the dark side, very long exposure. You can see the sky, actually. You can see a few stars there. And this is another picture. We took this one in Kenya ages ago when the solar activity was at the maximum. The activity of the sun goes up and down every 11 years. This was a maximum of activity. 6 or 7 years later, we took another eclipse from India, and look at the shape of the solar corona. You cannot see a magnetic field here. It's all over the place. It's very homogeneously distributed, but in solar minimum, the solar corona follows the magnetic field. The magnetic field kind of recomposes itself for the new cycle, and you can see the magnetic poles very clearly, and the whole cycle starts again. So this is a drawing made by one of our colleagues in the British Astronomical Association of the same eclipse. It's an amazing detail that he managed to get just by eye. So you see, you can quickly say this is solar minimum. All these are kind of solar minimum or semi-maximum. These are some drawings made in the 19th century about the polar plumes. These are obviously a solar minimum, similar to the one I just showed. Some other drawings of astronomers in the 17th, 19th century. And what we see today is a synthesis of the magnetic fields in the solar corona. All they are being modeled. All we have these computer animations of how the magnetic field in the solar corona interacts. And you know why? It's because we are immersed in the solar corona. So it's part of our environment, part of our, as we call it, the space weather. So an explanation of the space weather is a very, very descriptive here. These are videos taken by the SOHO, the Solar and Heliospheric Observatory, which has been in orbit for, in orbit around the sun. When was that? 1995, I think it was, more than 20 years ago. Still working. It produces a solar eclipse. Certainly, there is an artificial eclipse. You are in space. There is no atmosphere there. If you block the sun, you can see the stars around. I mean, you see stars and planets here. All these are stars. And the sun is blocked by an occulting disk, a kind of, it's called a coronagraph, inside the instrument. So the sun will be here. That will be the size of the sun. The disk has to be quite big because you have to have some tolerance there, because if your instrument moves a little bit, you can get the sun shining and then destroys the instrument. So you have to have that. Now, what you see here is the dynamic activity of the solar corona in a few hours. This is a coronal mass ejection that goes that way, but sometimes it comes this way. If it comes this way, there is no umbrella able to protect you or to protect the poor thing. This poor thing the detectors are saturated by cosmic radiation, by charged particles. You see the amount of damage that it can produce. When this happens, the SOHO sometimes is disconnected and wait for the solar storm to pass. But that is coming towards us because the spacecraft is between us and the sun. So we better know about these things. We have a lot of computer models to simulate and predict the shape of the corona. We have a lot of satellite, a lot of space observatories looking at the sun in different ways. But certainly it is an amazing chaotic part of the atmosphere of the sun. I'll show you this again to bring that into context now, and we are going to come to the end of the session just now. The shadow comes from here to here. You can see the difference in illumination and how quickly it goes. And still today, as I say, when you are witnessing that, you have this feeling, this emotion that we have for thousands of years before. The eclipses have a severe impact in young minds. They come with their own interpretations of eclipses. And we certainly worship the sun the same way as the pharaoh, Akhenaten, did, because we realize how important the sun is. The sun is in this beautiful picture, is looking after all what you have created. As the pharaoh said, we have all this enormous richness of complexity and diversity that we are very wisely destroying. So so you sat in the West, and we thank you for all your life that you have given us, and we wait for your appearance the following morning. And when we share the same landscapes with the ancient cultures, we travel in time and we see the same things, probably have the same feelings, despite of all our science. Isn't that amazing? Thank you very much. Thank you.
Well, thank you very much, Dr. Diego. What a lovely way to start a Saturday morning, I think, with some lovely images and poetry and videos. So thank you very much.
It's a pleasure.
We have about 15 minutes or so for questions. I'm happy to moderate this, gentleman, please.
A couple of questions, if I can be sneaky. First of all, I was going to ask what the battle was and who were the participants who went into armistice. And the second one was the magnetic field of the sun, I assume, is because of a moving plasma and moving charges, moving charge plasma in the sun itself. But I also understand it's on a 22-year cycle where the polarity of the field flips for the second cycle. So what changes in the sun in terms of movement of the plasma to swap the field round?
I have the details. I don't remember the details of the battle. It's somewhere in the Middle East, but it's obviously in the Middle East, okay? And it's still happening today. So magnetic fields are a major mystery. Astronomy is all very nice until you hit magnetic fields. The forces of nature that we know, the strong, the weak, and the electromagnetic and gravity, they are a big mystery. We know how they work, we have the equations, we have to explain properly in terms that we can understand. We still don't know why gravity works like that you leave things to fall. We still don't know. It's the curvature of space-time, and yes, but no. Okay? It's no intuition. I mean, one explains sound waves, it's easier to understand sound waves. The day we have an explanation of all these forces, the way we explain sound waves, then we are now proper understanding. So magnetic fields. The magnetic fields in stars and planets flip. We know the magnetic field of the Earth flips as well during a long period of time. The magnetic field of the sun also flips in a matter of hours, I understand. Why is that? The magnetic fields, kind of magnetic lines, they wind up and they start to produce this chaotic thing that manifests in the shape of the corona, and then it flips and the whole thing resets and becomes all organized again, magnetic poles, etc., and then the whole thing starts again. It is in a cycle of 11 years, but the whole flip, of course, when you go north-south and then south-north, is 22 years. It's twice that.
I just wanted to make a comment there that it's not 11 years like an 11-year orbit. So it doesn't come round exactly every 11 years. And in fact, the current cycle is deeply disturbed, so that the cycle, although the average is 11, if you look at the last 5, the first 3 of them were 10 years, the next one was 14 years, and the current one is back to 10 years. And we're now at the lowest level of solar activity that we've been at for 100 years. So this is really not...
it's not regular,
it's
absolutely.
not regular,
Yeah.
It's not easy to predict. People try to predict it in terms of the convective motions inside the sun. But at the minute, I know this to my cost, because I once, or twice actually, flew X-ray instruments to the moon, which relied on the sun being at solar maximum when it got there, and there it wasn't. It really is very hard, and if someone tells you they can predict when the next solar cycle is coming,
I say, magnetic fields are...
they're not, they haven't got it.
Magnetic fields are complete. I mean, a few years back, I made a special solar filter for a friend of mine that got a new telescope, and I said, here's your solar filter to look at sunspots. Where are the sunspots, please? Haven't seen any proper sunspots for years, I think.
It's very quiet.
It is, yeah. So that's completely unpredictable. That's what I said. It is it's a big mystery. Yeah. It's a big mystery.
I think it's unstoppable. The last minimum was the lowest in 100 years. Yeah. And this one is heading
that way. Well, it looks like it might tell us. Yeah. Thank you.
Any other questions?
Thanks. Could I just ask, the opening prayer, was that from the Book of the Day?
The open prayer is the hymn of To the Sun by Akhenaten.
By Akhenaten?
Yeah.
Thank you.
The next solar eclipse, I think, is next year in South America, and the following one also in South America. So, and the first one is going to be clear. I think the second one is going to be cloudy, according to the general predictions. So, there are total solar eclipses on average every year, every 2 years, somewhere on the planet. And then we have to travel and to see them, and we do. Yes, in the back.
I love the poetry that you've put along with it. I'm just curious, do you have a specific research interest when you're looking at these images of solar eclipses? What kind of signatures are you looking for? Is it just in general the magnetospheric aspect?
One of the projects I have been involved with, although I'm not a solar physicist, but some of my colleagues, we collaborated in different aspects in getting the images. They were looking for very fast, rapid oscillations in the inner part of the solar corona, kind of vibrations that are more visible in a kind of color that is emitted by atoms of iron that have been, at those temperatures of 2 million degrees, those atoms of iron has lost most of their electrons, and they are extremely ionized, and they produce this green line. And that's where the oscillation, this is called the fast, what they call fast period coronal oscillations that can be observed with very fast photography at that point. And this is one of the mechanisms that could be the ones that give the corona, combined with magnetic fields, give the corona the high temperature.
Resonances.
The resonances, yeah.
Thank you very much.
Yeah.
Yes, gentlemen. Down in the middle here. Thank you.
How susceptible to will our modern communications and communications across the Earth be to the next big coronal mass ejection that comes towards us?
The communications, what, sorry?
How susceptible will our communications and electronics and the internet and things be susceptible to the next
Well,
big...
yes, the solar storms are lethal, really. They can be beautiful when they strike the upper layers of the atmosphere in the polar regions here. You see the northern lights, the southern lights, the aurora, which is fantastic. But if that energy hits the SOHO spacecraft like that, a couple of satellites, communication satellites, have been disabled by solar storms already. And talking about this radiation that is now in a minimum, the Apollo astronauts were extremely lucky at that time because there were no solar storms that big. If they had been a solar storm big enough, they would have suffered enormous damage in their bodies, in mutations, radiation damage, cancer, leukemia, you name it. He was very lucky because you are not protected against that in a little spacecraft like that. That's one of the main problems of space exploration in the solar system. Going to the moon and Mars is going to be a major problem because we don't have a way of mitigating the effect of cosmic radiation in general, but the sun especially. If you have a solar storm, yes, you have a few hours of warning that the thing is coming, but you need to have a very, very good protection. This is why the lunar colonies and Martian colonies will be underground to be protected against. When you see all these beautiful cities on top of Mars, that's rubbish. It has to be underground. It has to be underground because you are not protected. We don't have the means to protect. Well, means are magnetic fields. Magnetic fields require enormous currents, electric currents, and you need enormous weight of metal to produce this current. So we haven't got the technology yet to do these things. But certainly it affects the magnetic field that comes into the Earth will destabilize electricity, the power grid. You send magnetic fields, you increase and decrease the current in those cables, brings it out of control and they trip. And then they self-protect and they trip. You have enormous blackouts in Canada, for example, in northern United States. It has happened 2 or 3 times. So it is very serious. This is why another main reason to study this.
Hi, just a little thought. Because we have got the solar activity that's low, and therefore the sunspots is low, I just wondered if we know what sort of temperature changes there might be on the surface of the sun that may or may not affect any sort of global warming that we're experiencing? I know we've got the carbon dioxide, but I'm just wondering if there was any significant changes in the surface of the temperature of the sun that might radiate out to the Earth?
No. No, there is nothing. No, there is nothing like that. The solar constant is pretty constant. I mean, we get, I don't know, say a kilowatt per square meter outside of the atmosphere. That doesn't change. With the solar activity, it may change a little bit. The solar corona expands a little bit and goes down. We know that that solar activity affects the level of our ionosphere. It changes a little bit. But to come to a more detailed effect in our weather, I think the answer is no, but there are better qualified people here to answer that question properly.
So we'll just go to the back for
yeah. I'm still confused about why the sun's magnetic field will flip. Why would that happen?
Why?
Why the sun's magnetic field would flip? Yeah.
Well, exactly. Welcome to the club.
Flip. I mean, why would that happen? I mean.
Exactly. Yes. I ask you the same question. You will be a student. You will be a solar physicist, and you answer that question in a few years. You get the Nobel Prize. It is a major mystery. Yeah, that's the open questions that we have.
Going back to the previous question about impact on the Earth with the solar storm, the Carrington event happened, it was pre-technology really, wasn't it? It was, I think there were telegraphs that were affected by it, and that was about it, wasn't it, I think, with the Carrington event?
Oh, the Carrington, that was in the 1800s.
Yeah. I was wondering, was there any other impact noticed on the Earth or attributed to it, either geologically speaking or climatically speaking, other than the views and obviously the aurora? Was anything else tied to the Carrington event?
Well, as far as I know, no, but I haven't investigated that.
Okay.
But I don't think there was, because we will know that.
Okay.
Yeah.
Just a thought, yeah. Sorry.
I think this will be our...
Well, it was just a comment on the original or an earlier question about the effect of changing in the fact that the solar activity is very low at the minute, and the solar cycle is low. And what is the effect of that on the Earth climate? It does have an effect, and it's the opposite way, or it's the same way as you think. It's that if the sun is a bit low, then its heating effect on the Earth is a bit low. And so rather than global warming, we should be having global cooling. And that it's about 1 part in 1,000 that the solar constant goes down. In other words, the solar constant is about 1 kilowatt per square meter at the Earth. It's about 1 watt per square meter as the input goes down. So what that actually tells you is that I hesitate to use the word, but human-produced global warming is actually worse than you might have thought. It's the sun, the solar low activity should be cooling the planet down.
Anybody have any further questions? Yes, this will be our last question.
Just one tiny one. I suppose the worst time to have solar storms is when the Earth itself is having a magnetic reversal and no magnetic field to protect us.
Well, yes, that is... No, yeah, we have been thinking about that, because it comes to the point where the magnetic field of the Earth flips. It kind of disappears. We lose our protection. The magnetosphere changes drastically, and then it reconfigures itself, I don't know, in a matter of a few hundred or a few thousand years, I don't know exactly. But then, now these things have happened, oh dear, is it again, unpredictable, but I think it's the order of 2 million years, something like that. So we have enough record in our geological record to see if there is any effect of those flips. All we have is in the ridges, in the oceans, we have the ocean floor is being replenished by submarine fissure eruptions. that follow the magnetism of the Earth at that time. And we see this kind of symmetric north-south, north-south, north-south that indicate the flips of the magnetic field. But apart from that indication, it doesn't look like there is anything else, I mean, affecting essentially biological evolution, mutations, or no big effect. I would expect that it will be, because you imagine you get rid of the protection for several hundreds, a couple of thousand years, and then the sun is still very active, and the cosmic rays come from all over the place as well. But yes, if you combine the decrease here and the increase there, I don't know. Probably, yes, but there is no evidence for that, I think. I mean, there may be something I'm missing, but yeah, it's a very good question.
Great. Well, thank you very much, Dr. Diego, and please join me in thanking Dr. Diego one more time for getting us off to a great start today. Thank you very much.